Module 2 is on compound stresses. Compound stresses. Compound stress. So in the module 1, what we have studied, an object is only subjected to a single stress. It was only a single stress. Either it may be a shear stress or it may be a normal stress, right? So it was that type of system. Here in this, compound stress is a one where an object is subjected to multiple stresses. This combination of a normal stress as well as a combination of shear stress. So we have studied there are different types of stresses, right? Like normal stress, shear stress, bending, right? So here an object is in a practical system, it is not only subjected to a single stress, it is always subjected to a multiple kind of stress. It may be tensile, compressive, shear, right? So altogether, all the stresses would be acting on a system. So if that is the case, so how to resolve it, the problem or how to solve the problems of that type, we are going to study here, right? So here basically first before starting, you should know the definitions of principal, definition of principal stress. So even this was asked, definitions could be asked, a principal stress and principal plane, right? So you know that there are two combinations of stress. One is normal stress, like it will be tensile or shear. It will be tensile or compressive stress. And the second, we have a shear stress. We have a shear stress, right? So the principal plane, first we'll tell what is the definition of a principal plane. Principal plane is the one where it does not have a shear stress. It does not contain a shear stress. The principal plane is the one, no shear stress exists in that particular plane. We call that as the principal stress. If there is no shear stress, there may be a normal stress, there may be compressive stress, there may be a tensile stress. If there is only a normal stress or other than shear stress, then we call it as a principal plane. Next, what do you mean by principal stress? Principal stress. Here in the principal plane, the shear stress will be zero, and if there is only a normal stress, the normal stress acting on the principal plane, we call it as a principal stress. The normal stress acting in a principal plane, we call it as, so this stress acting on a principal plane, we call it as a principal definitions. Okay, the basic definition. Next, in a compound stress, there are three kinds of systems or stress may be acting in a system. Like first type, it is you have a derivation for all the type. A unidirectional direct stress. You need to derive the expression for all these compound stress. There are first stress that is acting on a system is unidirectional direct stress. That is only a single stress acting in one direction. One direction. You know there are different directions like x direction, y direction, z direction, right? So in one of the directions, if the stress is acting, what is the system that is that all are different stresses acting? We are going to find the equations for that. Second type, it is a bidirectional or biaxial. Biaxial, biaxial direct stress. So that is, if the stress is acting on a same component in multiple axes, in x-axis and y-axis, or x-axis and z-axis, like any of the two axes, if the stress is acting, that we call it as a biaxial stress system. Next, the third type is we have a general two-dimensional stress system. That is, or we can take it as two-dimensional stress along with shear, along with shear. So that is, we'll do the derivation afterwards. So all the three derivations we need to do it. So that is, along with bidirectional stress, there is one more shear stress. There is one more shear stress if it is acting. The three different stresses are acting. That is one in x direction, another one is y direction, and another one in shear along the plane. If that is the case, so what is the equations that you're going to use that we need to derive it? So that we are going to study in this. So we have three derivations. Almost any of the derivations can be asked out of these three. So almost this is asked many times. The last one, that type it is important where they have asked many times, and also this has been asked. So you may get any of the derivations. So first we'll derive the expression for a unidirectional direct stress. Unidirectional direct stress. If you just understood this one of the concept, all the three it is similar. All the three it is similar. You need to resolve the forces. If you just understood the how to resolve the force, it is easier. Okay. So we'll derive it for unidirectional expression for, note down, a member subjected to unidirectional stress. Member subjected to unidirectional stress. So here let me consider object. So it is like a cube. So let me consider a cube. Whatever the theory I am going to tell, that has to be written by you. So it is. So we are consider a cube. We are consider a cube of some dimension A, some dimension A. So the sides of the cube is A. Okay. The sides of the cube is A, which is subjected to a unidirectional stress. So let me take a stress is acting in x direction, that is sigma or sigma x, sigma or sigma x, okay? Sigma or sigma x we can take. Since only one stress is there, let me take it as sigma itself. Okay. So for my derivation, what I do is, so I will consider this cube of unit thickness. So this thickness, let me consider it as 1 of unit thickness, and I'll just rewrite this sketch. So I consider this as unit thickness, so I'll be taking this only one of the plane. So I have considered this thickness as unit. So if this is the face AB, this is the face or ABCD, AB and CD. So let me consider this A, B, C and D, right? Okay. So I have considered a cubical plane, one of the plane in the cube, and this cube is having a unit thickness. This cube is having a unit thickness. So those theory part you should write. As I say, you can take down. So now I consider a cube of unit thickness. Okay, you take it. So now I need to derive expression for stress acting at some plane. I don't know. So let me take some plane here. So I'll take some plane which is inclined at certain angle inside the cube. So let me take some plane. The plane which is, I will name it as E. E. Name that plane as E. Okay. So it is, this plane is inclined at an angle of some angle theta. It is inclined at an angle theta. So consider some oblique plane EB, or sorry, what is that? EC, oblique plane EC at an angle theta to the cross section, So whenever it is not there, the plane is not considered, as we know, there are two, that is principal plane, it will be a principal plane. So there exists only a normal stress, the applied stress was sigma, so that I'm taking here, this is a stress sigma is applied. Now, since it is inclined at some plane, there always exists two stresses. One is a normal stress, another one is a tangential stress. So normal stress is always perpendicular. So to this inclined plane, draw the vertical. So draw the vertical. So just a perpendicular. So perpendicular is the normal stress. So that is, I'll take it as normal stress as sigma n. Normal stress is taken as sigma n. Next, on the inclined plane, there exist two stresses. One is a normal stress, another one is a tangential stress. So this tangential stress is along the plane itself. It is tangential to the plane. So plane is inclining in this position. I will take the tangential stress in the inclination direction. So it is tangential stress is sigma T. As the name itself, the tangential stress is sigma T. Tangential stress is sigma T. Okay. So here we have considered one of the rectangular portion, that is one of the plane in a cube of uniform cross section. Let the member be subjected to an axial stress on the section which is normal to the axis. This stress is normal to the axis. That it is a normal stress is acting here. And to derive the expression for a stress acting on an oblique plane or inclined plane, we have considered an inclined plane EC, which is inclined at an angle theta. So as it is inclined, there are two stresses generally acting on an inclined plane. One is normal stress, another is tangential stress. Normal stress is always perpendicular to the plane. Tangential stress is always parallel to the plane. Okay. So here you need to be careful to resolve the forces. So let me take whatever the direction we have considered here. So this has a positive. This direction as positive. If it is, so I am taken this normal force in this direction and tangential force in this direction. So this I'll take it as positive and this as positive. So if any forces, if it is acting in the reverse direction, I'll take it as negative. If it is acting in the reverse direction, I'll take it as negative. Okay. So if you take this as negative, this is considered as positive. Got it? Right? I need to resolve the force component for the uniaxial stress with respect to normal and tangential stress. So I'll resolve this force. So here we have this is sigma, right? So this is the actual force that is acting on a system. This is the actual stress that is acting on the system. So here I need to resolve this, whatever the stress that is acting. So resolution, it is simple. One component you resolve with respect to a tangential stress. Another component you resolve with respect to normal stress, right? So here, while resolving, the loop has to be closed. This is the actual stress with respect to the actual stress. So if this is the actual stress, it is acting like this. So if I'm resolving two components, so this will be one component, another component will be like this. The direction. The direction is very important. The direction has to close with respect to the actual stress acting. Right? If it is acting, you can also take to the other direction like this. Right? This should be a closed loop. It should be a closed loop. The concept to resolve the stresses. So here, so let me resolve this stress acting with respect to the inclined plane, that is a normal stress and tangential stress, with respect to normal stress and tangential stress. So let me resolve. So this is the tangential stress. So I'll take this along the this point. I'll take a resolve with respect to this initial point. So this is the tangential stress. It is going upwards. So since I need to close this loop, so draw the line parallel to the tangential stress. Draw the line parallel to the tangential stress. So this should be parallel line. This tangential stress, the line has to be parallel. So and the direction, since it has to close with the loop, the direction is in this direction. Got it? This is the direction. Next, you resolve another component with respect to normal stress from this point itself, from the ending point, from this ending point, you draw one more line parallel to the normal stress. One is parallel to the tangential stress, another it is parallel to the normal stress from the component. So you take a line parallel to normal stress, then draw it. So it should close this loop. So this is one method. So also for the same I will take it. So you can do it in other direction also. So first, this was the force. This was the force sigma. So now I'll take this normal stress first. Normal stress first. So I should draw the parallel line from the starting point. I can do it in the reverse direction also. So this line is parallel to the normal stress. Parallel to the normal stress. Then draw the direction arrow mark. Next, another line it is tangential stress. We should draw the point line parallel to the tangential stress from this ending point. So you can do it in this reverse direction also. Right? Got it? If you understood this, so all the three derivations, same concept, right? The fourth resolution is the main thing here. Fourth resolution is the main thing. You should resolve the force with respect to normal and tangential stresses. The concept is the loop has to be closed with respect to, it should be in the same direction. It should be either this clockwise direction or in the anti-clockwise direction. So whatever the resolution component you take, that is nothing but a parallel component with respect to normal stress and tangential stress. That's it. Got it? Now, so I should take an angle theta on the resolution component. So since this is theta, this angle is also theta. This will be theta, and this will be 90 minus theta. So if this is 90 minus theta, this will be theta, right? So this is not a geometry. If you are, it is with respect to the geometry of the figure. So this will be theta. This will be theta. Got it? So since this is theta, should be I think adjacent angle. These are theta. If this is theta, this horizontal, this angle will be 90 minus theta. So if it is 90 minus theta, this angle will be theta. Right? So now you resolve the component to sine and cos, right? So what is this component? The opposite angle. This is this theta opposite sine in the sense this component is sigma. So this will be sigma sine theta. So what about This will be, this component is cos. This is sigma cos theta. Got it? So if you understood this resolution of the force, it is simple. Next, only you should add sum of all the horizontal force, and that is sum of all the normal force and sum of all the tangential force to 0. You will get the expression. Right? So if you are confused, I can write this separately. I can take EB triangle. So I'll show it once again how to resolve. So this is the very basic step. If you understood this, then it is easier. So it is EBC. EBC is the triangle. So this is theta. So on the EB, on EC, so we have a normal stress, that is sigma n. And we have a tangential stress, sigma p. So here on BC, there is a unidirectional stress, that is sigma is acting. Unidirectional stress, sigma is acting. So I need to resolve this applied force with respect to inclined plane. With respect to inclined plane, we have two stresses. So resolve with respect to those two stresses. So start with any point, either take to the bottom side or so you take up it here. So you'll draw, this line is parallel to this tangential stress. So draw the direction. The direction has to close with the applied stress. So its direction will be in the reverse direction. Next. So I have drawn the parallel line to the tangential stress. Next, draw the parallel line with respect to normal stress with the ending point. So this is the ending point. So that has to connect with the applied stress, right? So this angle is theta. So this will be theta. So this will be theta. Then this will be 90 minus theta. So then this angle would be theta. So next, resolve the sine and cos component. So this opposite will be sine. So since this will be sigma, this will be sigma. So this will be sigma sine theta. And this adjacent will be sigma cos theta, right? So to not to be confused, I have shown it in the separate. Okay. So now consider the triangle. Resolve the force. Resolve the force. So resolve the force. Resolve the forces. That is, first we'll consider the sum of a normal force, that is Fn. We'll take it as Fn is the normal force to 0. Sum of all the normal force to 0. Sum of all the normal forces to 0. Right? So which is the normal force here? Normal force here, one to sigma act ಆಗ್ತಾ right? One is sigma. You know the definition for force is stress is equal to force by area, right? That is, stress is equal to force by area. So force is equal to stress into area. So what you have considered it is, this plane is having unit thickness. Thickness is unit, right? So now I need to consider the plane where EC, wherever I am going to resolve the force with respect to this triangle ECB. I am going to take the resolve the force with respect to triangle ECB. On the plane EC, we have the force acting. On the plane BC, we have the force acting, right? So the normal force on the plane EC is what? Sigma n, right? Sigma n, and its area is EC. Area is EC. Thickness is 1. We have considered it as unit thickness. I'll starting with the plane is of unit thickness. Unit thickness. So this first will resolve for normal force. Normal force is only sigma n is there in this EC. So it is sigma n into unit thickness 1 area. See here. Sigma into area. It is thickness is 1 and its plane is EC. So EC into 1 is the area. So I am taking this as positive. Whatever the force that is going in this direction, I have taken it as positive. If something is going in the opposite direction, I take it as negative. So there is one more. Whatever the force which is parallel to this force is the normal force. So this is the parallel component. So this is sigma into cos theta is the force. It is minus. Why it is minus? Why it is minus? This direction is in the opposite direction to sigma n. So this is the case. So I am taking negative. It is sigma sigma cos theta. This is the force, and its area is BC. Plane BC into thickness is 1 into BC into 1. Right? So this will be equal to 0. There are no other normal force. There are no other normal force. The other forces are only a tangential force. So now equate that to 0. Then cross multiply, just rearrange this. Sigma n is equal to sigma cos theta BC by EC. Right? Just I have taken this to other side. Sigma n is equal to sigma n BC by EC. A triangle that is BCE. Consider the triangle BCE. So what is BC by EC from the triangle? What is BC by EC? What is BC by EC from this triangle? So look at the triangle. So from triangle ECB, what is BC by EC? How much? What is that component? BC by EC. So this BC is adjacent. This is theta. Theta is EB is opposite. BC is adjacent to hypotenuse. It is cos theta, right? So BC by EC is cos theta from the triangle. So substitute that. Therefore, sigma n is equal to sigma into cos square theta. So this is the normal stress equation for unidirectional direct stress. Normal stress equation for unidirectional direct stress. So now we need to find it for tangential stress. This is the same. So now resolve, take sum of all the tangential force, that is Ft, sigma Ft is equal to 0. T is the tangential force. So here there are two tangential force. One is this, and whatever the force parallel to this is this component, that is sigma sine theta. Sigma T and sigma sine theta. Sigma T is acting in plane EC, and this sigma sine theta is acting in plane BC. So just take that. So that is sigma T. Sigma T is the stress. That is force is equal to stress into area. So sigma T is the stress. It is acting on the plane EC. Its area is EC into unit thickness 1. Unit thickness 1. So I'll take this direction as positive, this direction as positive. So whereas this sigma sine theta is acting in opposite direction. Minus sigma sine theta. It is acting on a plane BC. So it is BC into thickness is 1. Unit thickness is 1. That is equal to 0. That is equal to 0. So just rearrange this. So sigma t is equal to sigma sin theta BC by EC. So same BC by EC is equal to cos theta. So it is sigma t is equal to sigma sin theta cos theta. So I'll just add and divide it by 2. So add and divide it by 2. So there is nothing changed. So this equation can be written as sigma by 2 sin 2 theta. So this is the equation for direct stress. You need to remember, note down second module, the equation, which are the additional equation in the second module for unidirectional direct stress. Normal stress is given by sigma cos square theta. Tangential stress is given by half of sigma sin 2 theta. So you need to remember this equation. Okay. Next, you need to find the resultant stress. So if so, this is the normal stress, that is sigma n. So this will be the tangential stress sigma t, right? So there is some resultant stress that will be acting, resultant stress that will be acting. So that is sigma r, sigma r, right? So this resultant stress component, resultant stress, it is given by, so if you just draw the perpendicular to this, it is nothing but this will be sigma t. So this resultant is inclined at an obliquity phi. You need to find this phi. The resultant stress so in the problem they will ask you to find the resultant stress. It is given by sigma r. Sigma r is equal to sigma n square plus root of sigma n square plus sigma t square. It is given by root of sigma n square plus sigma t square. If this is phi, the obliquity, the resultant stress is inclined at an angle phi with respect to normal stress. So that is, if this will be sigma t, then phi is equal to tan inverse of sigma t by sigma n. So that we call it as obliquity. Obliquity phi is equal to tan inverse sigma t by sigma n. Also remember these equations. So from the equation, so if you substitute theta is equal to maximum normal stress, that is maximum normal. So whenever the stress is maximum normal stress exists when theta is equal to 0, right? Cos 0 is 1, right? And minimum, when you give theta is equal to 90 degree, you will get normal stress as 0. When you give theta is equal to 0, you will get normal stress a maximum. So that you write, the maximum normal stress exists when theta is equal to 0 and minimum normal stress when theta is equal to 90 degree. 90 degree. So when you substitute theta 90, you will get this normal stress a minimum. So similarly, tangential stress, it is sin 2 theta we have. So I need theta to be, that is sin theta to be 1. The sin theta will be 1 whenever it is 90 degrees, right? So it has to be 90 degrees, then theta has to be 45 degrees or 135 degrees. So this is the condition. So this is maximum when theta is equal to 45 or 135 degree, and it is minimum, when theta is 0 or theta is equal to 90 degree. So whenever theta is 45, this becomes 90. So sine 90 is also 1, sine 270 is also 1. Then theta is 0, then it is sine 0, it is 0. 90, it is also 0. So this is the condition for maximum and minimum tangential stress. So this is the simple derivation. Next, the force gets added. So this is a unidirectional force. We are resolved only for one of the stress component. If it is bidirectional, we will get one more stress here. This will be sigma 1, this will be sigma 2. Then you need to respect to this additional stress. That is the second case that will do. That will do in the next class, I think. So if you have any doubts here, you can ask. So if you understood this, if it is easier, you look at this lecture video. It is available in the Teams where you can view. Once again, you look at or you just refer with the textbooks. If you have any doubts, you just clear it now itself in the next class. So now if the stress gets added, this is the unidirectional stress. In the next, there is the bidirectional stress. There is one more resolution of the force, you need to do it. So along with horizontal, that is x component, you need to resolve the force with respect to y component of the stress, right? So that is the second derivation. So note down the equations, whatever we have got, that you need to apply while solving the problems with respect to the forces.